Hi everyone, and welcome to another Godot tutorial. My name is Ray, and today we're taking a first look at ARKit for Godot. While we've been working on this for a while now, this functionality is still in beta and may change. With this video, I'm hoping to get more people testing. If you're not interested in ARKit, this video might still be interesting to you, as we'll first be covering building Godot from source for both OS X and iOS. We'll then tackle exporting a project to an iPhone. At this point in time, you do need a paid developer account with Apple even to test your app. This is because Godot uses modules that have this requirement. In theory, you should be able to turn that off, but I've not gotten that to work correctly. In order to build Godot from source, we need a couple of things. Everything we need is already installed on my laptop, so we'll just run through them. Our main tool is Xcode. Without it, we can't deploy anything to our iPhone. Xcode is a free download on the Apple Store. This thing is huge, so make sure you do this in advance. We also need to tell Xcode to install the command line tools. Apple seems to love changing how this works between versions, so it's best to give this a quick Google. We also need to install Python. You can download this from the Python website. The latest Python 3 should work just fine. Next, you need Scons. Scons is a build tool written in Python which Godot uses to compile its source code. You have to dig through the documentation a little, but with Python already installed, you can simply tell Python to do the installation work for you. We also need the Godot source code itself. For this, I'm opening up a terminal and creating a new folder on my desktop. The easiest way to get the source code with the ARKit changes applied is to simply go to the pull request page and search for ARKit. Then click on the ARKit PR. This is a good place to read up on the current state of things, as things will change. If you can no longer find this PR, it'll probably have been merged and you can just use a nightly build of Godot. On the PR page, simply click on my branch to go to the fork of Godot I have on my GitHub page. Here you can download my branch with all the ARKit changes applied, or if you have Git installed, which I can highly recommend, you can use the terminal to clone the repository. In our terminal, we simply type in git clone, paste our URL, and add -b ARKit31 to select the branch. This will take a while to download. After the download is finished, we need to cd into the folder that was created. We need to start building a new desktop version of Godot, or we won't be able to set up our scenes in a way that makes ARKit work. We simply type scons platform equals OS X -J8. The -J switch enables compiling multiple source files in parallel and cuts down on compilation time. But even with the switch, this would still take several minutes on my MacBook. Our executable ends up in the Godot bin folder. We can't, however, double-click on this to run it. We can run our executable straight from the command line, but this is far from ideal. OS X requires us to package our build inside of an application bundle. Luckily, we have a template for this. Use Finder to navigate into Godot misc dist. Inside here, you'll find a file called osx_tools.app. We're going to copy that file into our root folder. Right or option click on the file and select Show Package Contents. This file is secretly a folder. That is the magic behind application bundles. Inside of this folder structure, we need to go to the contents and we need to create a folder called macOS. Watch the capitalization of the name. Now we need to copy our executable into this folder. I've quickly opened the second tab for this to make it easier. We need to rename our executable to Godot. Alternatively, we could create this as a symlink so that when we recompile our executable, our app bundle will always start the latest version. Don't take this approach if you're planning on giving someone a copy. Now you can double click on this and you'll see my existing project list coming up. This information is stored in my users folder, so I'm getting these from a previous custom build. Now it is time to build our iOS build, so back in our terminal we execute sconce platform equals iPhone target equals release underscore debug minus J8. The new switch tells Godot that we want a debug build. Because we're building for iOS, this is a build without the editor embedded. Don't worry about the platform name being iPhone, this works on iPads just fine. Again, we're in for a long compile, nearly 7 minutes according to my recording. Our compiled executable again ends up in our bin folder. The version we've built is a 64-bit version of the executable. For a full build, we should also include a 32-bit version and combine those in an archive. I will skip those steps because for testing we don't need this. Also keeping in mind that Apple is about to drop 32-bit support anyway. For releasing your game, you need to perform a release build, but for that just repeat these instructions but replace target with target is release in your sconce command. Just like our OS X build, we can't use these executables directly. We go back to our Godot misc disk folder. This time we copy the folder called iOS_Xcode to our project's root. This contains a template that Godot uses to export our iOS build. We need to replace our debug and release placeholders with our actual executables. As I haven't built the release version, I'm only replacing the debug version, which is fine as long as I keep performing debug exports. Note also the name of these files. FAT indicates an archive with both 32-bit and 64-bit builds, but we can just pretend to have that. Again, as long as we don't require the 32-bit build, the export will be happy. To complete our export template, we need to compress the contents of our template folder and rename this zip file to iphone.zip. Time to create a test project so we can see if everything works so far. We'll create a new Godot project and place it inside of our Godot ARKit folder. All we're doing in this project is set up a simple 2D scene. We add a button in this scene that we can press and we'll call this quit. I also adjust the scale to size it a bit. Let's save our scene and create a script on our scene. Now we can connect our pressed signal on our button. Note the new and improved signal dialog. It's so much simpler. Our line of code is simply getTree.quit. I'm quickly running this on the desktop to test if it works. This also ensures that Godot asks what our starting scene is. This is very important because the iOS export does not check this, and if you do not configure this, your application will fail to load without warning. I've previously wasted an hour or so on figuring that one out. Now we go to Project Export to set up our iOS export. Press Add and select iOS. It will give us a list of things we need to fix up before we can export. Normally, you would download the export templates from the Godot website. The editor has a nice built-in option for this download nowadays, but as we're using a custom build, we won't be using this. Instead, we select our iphone.zip file in the custom package section of our export settings. Next, we need an App Store ID. If you fill this in correctly, Xcode should automatically attempt to deploy your app to your phone as part of the export process. I'm going to fill in a bogus value here because I'm going to make the selection in Xcode itself. Next, we need to specify an identifier. Now this takes the form of com.companyname.GameName and is linked to your developer account. You need to create provisioning profiles for this, but again, we can let Xcode do the work for us. For now, I'm just going to fill in com.godot.test, but we will be changing this later on. We also need to tick ARKit in our capabilities. However, this doesn't make all the necessary changes yet, as we'll see. Last but not least, we need a couple of icons in different sizes. Bear with me while I create a few blank ones using Krita. Now we simply assign these and voila! Time to export our game. We now find a folder in our folder structure that contains a couple of support files, an Xcode project file, our executable, and our game PCK file, which contains all of our scenes, images, etc. We can double click on our Xcode project file to open up our project in Xcode. It will immediately start throwing up warnings and errors. If we select our root node in our tree list on the left hand side, we can see our project settings. If you don't see the tree list, note all the buttons that provide access to the different tabs here. Just select the first tab. Here is our first problem. Xcode does not have a clue who Later is, so we simply select a real account from the dropdown. Now excuse me that I will blur a few things out, as I don't want to give too much personal information away. We also need to change the bundle identifier as I mentioned before. I'm blurring it out here again, but as I said, it should take the format of com.yourcompanyname.yourgamename without spaces and special characters. Now one thing I forgot, and I will show this in a minute, is to disable 32-bit in our export settings. So at this time, Xcode is still looking for our non-existing 32-bit build. We can simply remove ARM v7 from our supported architectures in our build settings. Next we need to go to build phases, and in our link binary with libraries, we have to make sure we add our ARKit framework. If we have our phone or tablet connected, we should see it selected in our top toolbar. If you can't, you need to turn on developer mode on your device. This changes from phone to phone, so please consult the Apple help pages for that. I think Xcode will attempt to guide you through this, but I haven't done this in a long time. Now hit the play button and Xcode will compile our project and attempt to run it on our device. Not spectacular, but we've proven this works. Note that in Xcode you also see the log output of our game. There are actually a lot of tools in Xcode for debugging and monitoring our game. Back in Godot, let's scroll down to the tick box we missed. Down at the bottom we can turn off the ARM v7 support. I'm going to change our root node to a spatial because we want to do things in 3D. I'm also adding a canvas layer and placing my button underneath so our 2D items are handled properly. Not very important for our test, but good practice just the same. The next step should be very familiar to those who've watched my VR tutorials. Everything AR and VR starts with an AR/VR origin node which anchors our real-world reference point to our virtual world. We also need an AR/VR camera, which is a special camera whose position and settings are fully controlled by the AR or VR system. As we move our phone in the real world, the camera will automatically move in the virtual world. Our virtual camera for rendering 3D content is one thing, but we also want to use the real camera on our phone to show the real world in the background. That is what makes AR, AR. For this we need to set up an environment on our camera node. It's easier to do this here, so that our default environment is still used in the editor, else things turn very black. In our background tab we select the new option Camera Feed. This lets us link the camera to a camera feed. This is actually part of a larger bit of functionality we added to Godot to allow things like webcams to be used in Godot. Don't worry about setting this up because ARKit will provide us with the correct feed. Do note that ARKit does a lot more than we currently support. For instance, ARKit is able to provide us with a radiance texture to perform indirect lighting. Stay tuned for this in the near future because we do intend to implement this. We also want something to actually see, so let's add a simple mesh instance with a cube mesh. For ARKit, all the units are in meters, so our cube will currently be 2 by 2 by 2 meters. Let's make that a little smaller and move it away from the camera a little. Now we need to edit our script. Again, those who have followed my tutorials before should recognize the following code. We start by creating a variable called ARKit. Then in our ready function, we use the AR/VR server to find our ARKit interface. If we find this, we'll attempt to initialize it. If that works, we're going to turn our viewport's AR/VR mode on. And finally, we are going to set the camera feed in our environment to the camera feed provided by ARKit. Before we can test our changes, we also need to change our extends from Node 2D to Spatial, seeing we've changed our main scene to a 3D scene. We go back to our export window, but instead of exporting our entire project again and creating a new Xcode project, we can take a shortcut. We can use the Export PCK button to simply export our game files and overwrite our PCK file. Now we return to Xcode and press the play button. As you can see, we now have a camera image in the background, and somewhere right through my wall is a very dark cube. Apologies for my messy desk. I share this desk with my kids and don't have a whole lot of room here. In Xcode, in our project settings, you find a number of tick boxes that specify which orientations we allow in our game. Our canvas will automatically be rotated and resized to adjust to these settings. However, they need to work in unison with another setting in Godot. In our project settings, if we go to Display and then Window, we find a setting called Handheld Orientation. This defaults to Landscape, which basically locks our screen in the landscape position. There are a number of issues resulting from this mismatch. Now we can return to Xcode and untick the options that don't apply, and this is actually the better solution in most cases, as it removes some overhead from your game. Alternatively, you can go back into Godot and change our orientation setting to Senza. This will result in Godot adjusting the orientation according to the allowed orientation set in your Xcode project. If you have a 2D UI that you want to reorientate depending on whether the user holds their phone upright or in landscape, you'll want to use this. Our cube was placed far inside of my wall because it's placed about a meter away from our starting location. My wall is about 40 centimeters away from my face. That won't do. Let's resize our cube to be a lot smaller and move it about 20 centimeters from the camera. Let's also add some light to our scene. We don't know where the real-world lighting comes from, and we haven't implemented our indirect lighting yet, so this won't be accurate. For now, it will have to do. Let's export our PCK again and see if our changes have worked. Now when we move our phone, we see that our code is nicely anchored a few centimeters in front of us. It's a shame I haven't got a second camera to show this, but I can move my camera around the cube to view it from its various sides. The tracking is pretty damn decent. Now this is all nice and all, but we really want to interact with what's really around us. ARKit will continuously attempt to interpret what the camera sees and detect surfaces like my messy desk and the wall. We can tap into this information, but we need to do a little bit of work for this. Looking into our AR/VR interface help files, we can see that we have a property called AR is Anchor Detection Enabled. This needs to be turned on to tell ARKit to start detecting surfaces. When ARKit finds a new surface, this is communicated to AR/VR server, so let's have a look at its help page. Surfaces and other objects that are detected in the real world are represented by anchors. In AR/VR server, entities such as track controllers, base stations, and anchors are all represented by a tracker. You can see that we can connect to signals that will be emitted when a tracker is added or removed from the AR/VR server. The second parameter here will tell us what type of tracker we're dealing with. We can find their definitions a little down below. We are interested in trackers with the type tracker anchor. So let's start with adding a couple of placeholder functions in our main script. One for trackers being added, and one that will be called when a tracker is removed. Now we can connect to our signals in our ready function. We also enable our anchor detection at the end of our ready function. Before we implement the rest of the code, we're going to create a new scene that we can instantiate for every anchor we find. We set this scene up as a 3D scene, but change the type of the root node to AR/VR anchor. As with most AR/VR nodes, this always needs to be a child node of our AR/VR origin node, and Godot will warn us of this. Let's quickly save our scene and call it anchor.tscn. We want to be able to see our anchors while we test, so we'll add a mesh instance child node and create a simple cylinder shape. Again, our default sizes are way too big. In our main script, we check if the tracker given to our tracker added function is an anchor. If so, we want to instance our scene. For this, we will add a variable to our script into which we preload our anchor scene. Now we create a new instance of this scene. We add this to our AR/VR origin node, but leave some space as we're not finished setting it up. We want to give our anchor node a name so we can easily access it. We then set our anchor's anchor ID to the ID that was parsed to us. This binds our anchor to our tracker and will ensure ARKit continuously updates its location. While anchor detection is turned on, ARKit will continuously update the anchors it finds when it learns more about the environment. When we start our game, only a fraction of my desk is in view, so ARKit isn't yet aware of how large it is. This also means ARKit will remove anchors when it finds out two anchors track different parts of the same surface. For this reason, we thus quickly implement our removal code as well. Here we simply find our anchor node by name, and if we find it, we queue free it. This is the safer way to remove nodes from your scene. Let's export our PCK again and start our game. The first surface ARKit finds is part of my laptop's monitor. A big circle suddenly appears. It's not long before it finds other bits of the environment. Circles aren't very handy, however. Luckily, ARKit can provide us with something far better. It will attempt to construct a low-poly model of the surfaces it finds. So let's remove our circle and add a script to our anchor scene. Looking at our anchor node, we find a signal it emits whenever the mesh associated with our anchor changes. This actually changes a lot in the beginning as ARKit learns more about our environment, so be aware of that. We connect the signal to our script. Let's clean up a little. In our mesh update function, we simply assign the mesh provided by ARKit as the mesh for our mesh instance. We do, however, want to be able to set a material to use for this mesh. We'll do something special with this material in a future video, but for now, let's do the groundwork. I'm adding an export variable so we can set our material on our scene. Then, in the setter for this material, I apply the material to our mesh instance if we're inside of the tree. Okay, that last one is a little funky. When our scene is instantiated and our setter is called for the first time, our mesh instance hasn't been created yet. This only happens once our scene is added as a child to our AR/VR origin node. It is added to our scene tree. Our origin node is already part of this tree. So a node being inside of the tree means that it's all up and running. Our getter simply returns our material. When our mesh is set, we also need to reapply our material as this will be cleared. Finally, we create a default material for our scene. Let's export our PCK and run. As you can see, ARKit is slowly making sense of my table. Now we're only drawing these shapes to visualize them. In a future video, I'll show how we can use this to cast shadows on our table. For now, I'm just making our material somewhat transparent. We are going to use our physics engine to interact with our surfaces. That means we need a static body and a collision shape. We can generate our collision shape from our mesh, but since Godot doesn't know what type of data is being parsed by our signal, it's not helping us find the right function. Let's use Godot's new static typing to tell it that we're getting a mesh here. Now Godot shows us the available methods. Thank you, Godot. We return to our main script and will implement an input event here. When you tap your finger on the display of the phone, this will be translated to a mouse pressed event. We thus check if our event is a mouse button event and whether the button is pressed. We need access to our camera, so we just obtain it from our current viewport. We could also just access the camera through node notation, but this makes the code a little more portable. Now we're going to be working directly with our physics server. This bit is a bit convoluted. We need to get the physics space of the world our camera belongs to. This allows us to get the state object for this space. It is with this state object we can query our physics engine. We're going to cast a ray from our camera based on our event position. Our camera has two handy functions to help us here. Project Ray Origin will tell us the 3D location associated with the 2D location where the user pressed on the screen. Project Ray Normal will tell us the direction from which the light hitting the pixel at this location came from. Now we can call the function Intersect Ray on our state object to cast a ray and see what surface it hits. If we hit a surface, our result variable will be a dictionary with information of where the ray hit and what it hit. We are only interested in where. We create a new transform variable and set its orientation to this position. Now we use the transform to set the global transform of our cube. This will place the cube in the world where we press the screen. Since the transform of the cube is centered on the center of the cube, we need to add half the height of the cube to the y of our transform. Now we export our PCK again and test on our iPhone. As you can see, I can change the location of our cube by pressing on the screen. That's all I have time for today. I hope this provides a good starting point. Remember, this is a beta and there is still plenty to fix and improve, but we do hope to merge a version into master soon. I plan to do additional videos to follow up on this in the near future, and we're nearly at a point with AR Core that it needs a similar video as well. Please follow me on Twitter for regular updates. I've joined Patreon. I want to raise some money to support the tutorial videos I make here on YouTube, so I can pay for assets I want to use to improve the quality of my tutorials and maybe get some additional recording hardware. My YouTube videos will remain free and I have no wish to change this, but if you like what I do and are able to support me, please consider joining as a patron. As always, if you found this video useful, please consider subscribing to my channel and hit that like button. Until next time.